Okay, now we're going to get into something that I found fascinating when I first learned about this. And that is something called KC. Now, K comes from the German word constant, which begins with a K instead of a C. The C means concentration in moles per liter. And so what we're going to look at is the relationship between the products and the reactants that turns out to be constant as long as the conditions stay the same, meaning pressure and temperature. If you don't change pressure and temperature, the reaction is going to move mainly to one side or the other in a distinctly mathematical proportion that I found baffling. Now, because it's concentrations, this is dealing only with aqueous solutions where everything is measured or can be measured in moles per liter, and in gaseous solutions, whose density is measured in grams per liter, but that is also considered a concentration as well. So anything liquid and solid cannot be part of this system. And I'll address one issue with that later on. But it's a very simple process. The K, in this case concentration, and we're going to express everything in concentration form using brackets. But it turns out that if you have a ratio of the products divided by the product of the reactants, in other words, you're multiplying the concentrations at the top and the bottom, that value is a constant. It's going to be the same. Again, not changing temperature or pressure. So, if you look at that, the concentrations of these products here, this is the concentration of NO2, those brackets mean concentration, times the concentration of NO. Divided by, now you put this in your denominator, concentration of N2O3. And that's going to equal some value, and we're going to talk about that in the next video or lesson. Now, I'm going to do something this you're not going to have to do. I'm going to show you why we do what we do. So, if we have two H2S's, I can rewrite that as H2 gas, H2S gas plus H2S gas. Hydrogen sulfide is a really noxious gas. And if you've ever eaten eggs or too many eggs the next day, you know that other people know about it. Woo! Bad news. But anyway, we have two hydrogens here, so we got hydrogen gas plus hydrogen gas. And then sulfur, going, wait a minute, you never told us that sulfur is diatomic, and that's correct. There are certain temperatures where a sulfur creates what we call allotropes, and it's different shapes according to temperature. And sometimes it is diatomic, not very often. It's at a distinctive range of temperatures where this occurs. But this is S2 gas. And as you see, it's gaseous sulfur, and that's commonly how we find sulfur in diatomic form. Now, the reason why I'm doing this will become evident here. And you won't have to write this out. This is showing you why things fall into play the way they do. So that means, according to KC, what we did up here, this is going to be concentration of H2 times the concentration of H2 times the concentration of S2 all over the concentration of H2S times the concentration of H2S. Now, who wants to write all that stuff down, right? So that's what God invented Expo, or whoever invented it. I believe it might have been some Indian mathematician who actually came up with that concept, but I'm not 100% sure on that. But regardless, we can turn this into H2 squared on top times S2 over, and we got two H2S's here that are multiplying together, so that becomes H2S quantity squared. Well, check out what just happened here. You have a 2 for a coefficient here, and that becomes an exponent here. You have 2 for a coefficient here. I hate this board so much. And I'm sorry, I just circled the wrong thing because I got mad at the board. So we got this 2 here. I don't know. And that's going to become the exponent here. So, bottom line is, whatever coefficient you have in an equilibrium expression, when you write the equilibrium expression in terms of K, you're going to change those coefficients into exponents. Okay? OKC? I like Oklahoma City about never. Now, we're going to go the other direction for problem number 29. Problem number 29, they're going to ask us to come up with a chemical equation based upon the case expression. This side is ridiculously easy. Okay? Now we know that these are the products. These are the reactants. So, reactants go first. We've got H2S. And these are gases, I'm going to assume. I know that these are all gases, except for this, and we'll talk about that just a little bit. As I said, well, liquids never go into these things. Campbell, there's a liquid out there. Hush, child, I will explain. Stop bothering me, let me get done with this lesson. So we got H2S here, but we got exponent of 2 here, so that means it's going to be a coefficient here. Plus O2, exponent 3 becomes coefficient of 3, it's gas. Then we come up here right now, here we got this. Now the fact that we can't have liquids in the equation means that this is not water, this is actually steam, it's H2O gas. And we have 2 of those babies, 2 H2O gases. Plus, and we got 2 sulfur dioxides. And there's your equation. They're all gases, and if you wanted to check, they balance out. I don't want to check because the book did this, and it's not right. It's their fault, not mine, so I'm not going to waste any time on it. Okay, the last problem, number 31, we have this Kc value or expression here, and they want us to take the they want to know what the expression is going to be when the equation that this is based upon is halved and then reversed. Okay? So, remember, these are the products. And these are the reactants. Okay, so this becomes 2 N2O5 gas, double arrow. Equilibrium, and then these right here, 4 NO2 gas plus O2 gas. Now I'm going to tell you, you don't have to do it this way, but I'm showing you at least where all this comes from. You want to do it the shorter way, that's fine. If you feel better doing it the long way, I have no issue with that. As long as you just show me what you did, which way you went. Okay? So, first thing you want us to do is halve everything. So, half of 2 is 1, so we just leave it like that. Half of 4 is 2. And then we put a 1/2 right here. It's half of 1 is half. The next thing you want to do is reverse the reaction. So that means 2 NO2 gas plus 1/2 O2 gas, double arrow, and then N2O5 gas. Okay? So, now we're going to write the Kc expression based upon this. So Kc is equal to the concentration of N2O5 over concentration of NO2 squared, because of that 2, times the concentration of O2 to the 1/2 power, which of course means it's the square root of that concentration. So there's your answer for that. So that's your Kc expression for that problem. However, did you have to go through this part here? No, you didn't. If you just follow the instructions, you'll see what I mean here. So it says here, Kc expression of the equation is half. Well, look what happened to the N2O5. It went from 2 to 1. All right, so because the coefficients get halved, that means the exponents of Kc is going to get halved. So that becomes 1, this becomes 1/2, and that becomes 2. Then it says the reaction reverse, which means products become reactants, reactants become products. Well, N2O5 is on the bottom here, it's now on the top. NO2 and O2 are both in the numerator. They were originally in the denominator with their new exponents. So that's all you have to do is change the exponents if the coefficient change, and then if the reaction is reversed, you just flip the equation. It's the reciprocal. Okay? Alright, so either way, fine. Your practice problems. I forgot to write down, because I'm clever that way, is pages 684, 685, and we're going to do 28 through 32.